A star has a long and complex life that we will explore in this video. First, let's talk about the birth of a star. A star starts as a nebula, a large cloud of gas and dust, and then the mass's gravity pulls this matter together, contracting into a cloud clump called a protostar. This is the earliest stage of the star's life. When the gas and dust become so hot, as gravity builds heat and pressure, nuclear fusion starts and the star is born. Then the star lights up and is illuminated. What is nuclear fusion? Nuclear fusion is when atomic nuclei, like deuterium and tritium, basically hydrogen isotopes, with one proton fuse to create helium, a neutron, and energy. This is the equation for nuclear fusion. How does nuclear fusion create energy in the core of stars? Inside the star, gravity pulls inwards, colliding hydrogen particles together. Heat and pressure builds, colliding the hydrogen more frequently with greater force, leading to nuclear fusion. The mass from the hydrogen gas is lost when it's fused into helium because it's converted into energy. The net gain in energy from nuclear fusion is large, causing the star to light up. By observing the light from the star, we can use the speed of light to determine when the star was born. Next, how do we know what stars are made up of? EM radiation consists of waves of the electromagnetic field that we observe. In the EM spectrum, there's a continuous whole range of wavelengths of light. We can analyze the color spectrums using spectroscopes. Different substances glow different colors in a flame test, so different elements have different emission and absorption spectrums. There are bright lines or dark lines that are associated with predictable wavelengths. These unique lines are a precise way to identify the elements. So, we can find the dark lines in the star's absorption spectrum and then match the emission spectrum of lines of different elements, or vice versa. Then we can see what materials the star is made up of, giving us a better understanding of its origins. Next, the main lifespan. Stars spend most of their lifetime in the main sequence stage. This is when they use hydrogen in nuclear fusion to create helium and heavier elements. The star is turned on and most stable during this stage. Smaller stars spend more time in this stage, whilst higher mass stars burn out quickly. Smallest main sequence star is a red dwarf, which is the most common in the Milky Way. This is an HR diagram. The y-axis shows luminosity from low to high, and the x-axis shows temperature from high to low. The position of the star on the graph is determined by its type, whether it's a dwarf giant or in the main sequence, and also based on its temperature and luminosity. How are mass, color, temperature, and luminosity related? The temperature affects the color of the star, as we see in the graph. The mass also affects the luminosity. Higher mass stars are more luminous. And the colors go from hot to cold, which are blue to white, yellow, orange, red, with blue being the hottest and red being the coolest color. More luminous stars are also higher up on the main sequence towards the left, which are in the blue color. They are very hot and bright, and the less bright stars are towards the bottom right of the main sequence. This just means they are usually smaller in mass. By looking at the luminosity of the star, we can also see what part of life it is in. If it's in the main sequence, pre-main sequence, if it's a red giant, etc. Mass and lifespan. Lifespan depends on the mass of a star. Larger mass stars live shorter because more gravity leads to more elements fusing faster due to more pressure. When a large mass star dies, it becomes a red supergiant and then goes supernova, which may form a neutron star or become a black hole in the future. In short, high mass equals high gravity, which is more hydrogen and more fusion. So the high mass star will use fuel fast and die out quickly. Smaller mass stars are the opposite. They have less gravity, so nuclear fusion happens at a slower rate, so they live longer. Also, high mass stars make heavier elements through nucleosynthesis. Nucleosynthesis works by combining protons and neutrons from nuclei of lighter elements, so hydrogens become helium, heat, and radiation in the star. With the higher mass and more gravity, more heat and pressure for fusion can make heavier things like iron, which is the heaviest element possibly made in the core of a star. Lower mass stars don't have enough gravity to make such heavy materials. Stability of the star. Outward pressure from this nuclear fusion is balanced with inward gravity to keep the star stable in the main sequence for a long time, as both forces continue to balance each other out, so the star is in equilibrium. When a main sequence star starts to run out of fuel, or when a main sequence star runs out of fuel, it collapses into itself, then expands as it loses control of its outer atmosphere. Then it turns into a blue supergiant or a red supergiant, etc. Finally, the death of a star. Aging stars run out of fuel as they do nucleosynthesis and nuclear fusion their whole lives. So the forces on the star at the end of its life are unbalanced and not in equilibrium, which causes the star's shape to shrink and expand, as gravity pushing outwards or inwards and fusion force pushing outwards are not equal. Class. Some stars are giants or dwarfs because they're not in the main sequence stage. Then they aren't going through nuclear fusion. Some stars become red giants, some become red supergiants, all depending on mass. So for stars with similar masses to our Sun, which are low and medium mass stars, they become red giants as they lose hold of their outer layer after nuclear fusion stops. So the outer parts expand and drift outwards, making a planetary nebula gas cloud. The core left behind cools down, and it becomes a white dwarf, which is very dense and hot. When the white dwarf runs out of fuel, it becomes a black dwarf, so it loses its luminosity, so light can tell us how old it is and how long ago it died. Higher mass stars than our Sun become red supergiants, which explode suddenly in a supernova. When the big stars make an iron core, and the rest of the star collapses due to high gravity, this material bounces off the core and sends out a big shock wave, so outer parts of the supernova are blasted away, which is a very quick process. This process can outshine its whole galaxy because the explosion has so much energy and is so bright. All that's left is the neutron star, or a black hole. So some materials left behind can form a neutron star, which is super small and dense. For the most massive stars, the left behind core becomes a black hole because a large mass remains, and gravity is so strong it pulls everything into a tiny space so that nothing, even light, can escape. Supernovas can make heavier elements. Fusion creates heavier and heavier elements because high pressure and heat combines protons and electrons to make neutrons. They combine with elements present from nuclear fusion to make heavier elements. Heavier elements also absorb leftover protons, becoming gold and copper and silver, which are very heavy elements, heavier than iron. Supernova pressure merges protons and electrons, making neutrons, making gold. Then the supernova explosion propels the gold and these heavy metals outwards with a shock wave. This is the process of nucleosynthesis, which is the synthesis of atoms and how they are sent around our universe. We are all made of stardust because all elements on Earth were created inside a star at one point. So we are all stardust. Small stars only make light elements, and all heavier elements than iron are made in supernovas. So all Earth things are made of carbon, which are too heavy to be made by our Sun. So that means we were made by the explosion of another star. Thank you. And that's a bit about the life of a star.